Welcome today. Our webinar today is 6 dry wood chip projects reviewed and an introduction to PDCs, the precision dry wood chips that Wheelen Energy manufactures and delivers here in Southwest New Hampshire up into a tri-state area of Vermont, New Hampshire, and Massachusetts. We are going to just be talking about the PDCs in an abbreviated format. And if you've seen this before, I apologize, but I think it's smart to give you that kind of quick introduction. But we'll get into the projects here pretty quick. And it's an interesting grouping of them, not necessarily our newest, but a good selection of them that shows some good variety. And I think you'll enjoy that. I am the VP of Sales and Marketing in Whelen Energy. Been here since 2012. And I've been involved in renewable energy for about 25 years, with starting in solar back in the 70s, believe it or not, and then ended up coming back with biomass here after a little reprieve into software and that sort of thing. So, but I grew up in the Midwest and always had a strong interest in energy conservation and alternative energy, especially. I've been in this Monadnock region around Peterborough, where our headquarters is right now, for a good long time. Wheelen Energy installs biomass boiler systems. That's really our business. And we got into fuels a little bit after getting a lot of installations and starting to see the installations getting bigger and bigger. The focus has always been on schools and campuses, but we do a lot of commercial buildings, industrial buildings, and we've done a few multifamily buildings that are quite appropriate, where anything that's centrally heated is really what we're looking for. If we had individual unit heaters, it doesn't become very practical. I should say individual boilers for individual units, but to have something centrally heated really makes a lot of difference. So next, just what we do, just to talk about retrofits, new construction. We clean the boilers, we service the boilers if there's breakdowns, and we also manufacture and deliver these things called PDCs that I'll tell you more about. We're self-performing. In other words, sometimes we bid as a GC, especially if it's just a project where there's a boiler room renovation or perhaps an expansion or a new boiler building. We'll build that building and take care of everything as a GC. But if it gets beyond that, there's other GCs that handle that much better. So if it's mainly focused on mechanical systems, that's what we do, and getting to project management and coordination of crews and so forth. And system commissioning is a big part of it. So today I'm going to talk about the 3 wood fuels that are out there, and we're going to talk then how they compare to the PDCs and how the PDCs are made and what they're all about. And then we're getting into dry wood chip boilers and a little bit of financial comparisons, but mainly we're going to review these 6 fuels, 6 installations, 3 biomass fuels. They're automated boiler systems. That's what it's all about. You don't want to have to be loading things in any kind of manual sense. So the automation is key. And these are readily available in northern New England, especially in this tri-state area where we are. The 3 fuels are wood pellets, screen semi-dry wood chips, and green wood chips. The first has been around here a long time, the green wood chips. In Vermont, they've been installing green wood chip boilers for at least 30 years in schools, and probably before then. Wood pellets came along when they started to manufacture them in bulk in our region, and that was in the range of about 10 to 15 years ago. And the dry wood chips we started up about 7 years ago. Start out just what green wood chips are. It's basically a tree that gets chopped up, so it's got 35 to 50% moisture. It ranges just by time of year. There's a chipper like this. It's chipped on site, and very often, sometimes there's not just a landing, but it's a place where a big logging company has a lot of wood stored, and they'll chip it there. But most often, it comes right out of the woods at a project where they're working with a forester and doing thinning or selective harvesting and making the forest good for the next 20, 30 years. But here's that idea of it's a wide size variation because the quality control is just as much as they can do. There's no screening typically. It's whatever the chipper kicks out. And there's always a little, the early part of a log and the last part of a log can be, a little bit more rough, just as it goes. So there's a lot of chip size variation. Percentage of bark is possible depending on how the guy sorts things. Generally, you can specify bullwood or you can go with whole tree chips or whatever, but the quality is a negotiation between you and the logger. So that's done on the site. And that's the source of everything pretty much. Like wood pellets, a lot of wood pellet content comes from green wood chips coming directly out of the forest. But the difference between wood pellets and dry chips is that moisture content, number one. And then the small size is actually, they're compact. They're about at least half the size of what wood chips would be. And that doesn't even really talk about the content of moisture, which detracts from it. So this being very dry and very compact, it's a great fuel for any place that is tight on storage. So quality is assured. It's a manufactured product that you can see. Here's there's trucks coming out of the woods here. Here's a log truck delivering logs right out of the woods, and then they chip it here. That's not quite as common, at least in our region. But they'll also get sawdust delivery from manufacturers and wood shavings from manufacturers, different sources. This could be a lumber operation that's bringing sawdust. And so they combine all these ingredients, hardwood, softwood. Each pellet company has its own mix. They'll take it through a hammer mill, and then they'll compress this. Once it's down to powder, everything turns in from a chip into a shaving down into powder, basically fibrous, and then they compress it in these pellet mills. It comes out and ends up going either to bulk or to bags, which we all have seen everywhere at every lumber yard in the fall. And then the pellet trucks, you might not have noticed the pellet trucks. They look like an oil tanker, and they'll deliver bulk. So what are dry wood chips? Well, they're 25% moisture content. They're right in between the two. It's still a varied size because it is a chip. We haven't tried to reconstitute it in any way, but we've screened out the big stuff and some of the fines as well. So there's an assured quality factor here of that 25%. And if this is aimed at the middle market, that just means that there's mid-size fuel users. It's not a small residence. It's not a small business. You want to have, maybe you're burning 10,000, 20,000 gallons of oil. That starts to become a perfect spot for us to start talking about dry wood chips. So that middle market. And then if you're a giant, if you're a campus, you're not going to burn dry wood chips. You're going to burn green wood chips. It's worth the investment in equipment, but we'll get into that a bit. But it is 35 to 50% less costly than wood pellets, and that's one of the driving forces is price. Here's how we make them, real straightforward. This guy's come right out of the woods, just in that landing that I showed you, or one of many hundreds of landings, and it's on a live floor truck, so they just drop it off the back of the truck. That's the way wood chips, I should say, are delivered most typically, is it comes off the back of a live floor truck. So it needs gravity to just drop off the back, and then you need to manage it somehow. And that's one of the things about green wood chips is that you have to have a pretty hefty system to manage those chips to get them to the boiler. Here, what we do is we drop them off the truck and then we put them through a screener, and here's the screener. And we get rid of all those oversized. We're looking for something about this big as an old-fashioned matchbook. And there we go. We get them after screening. They look a lot cleaner. There are fewer odds and ends of sizes, and plus the thickness and everything. It's all now able to go through the smaller augers that a dry wood chip system would have. Then we dry it down to 25% moisture once we've screened it. And this is a belt dryer. It's about 75 feet long, and it goes in, chip comes in 45% moisture, say, comes out 25% at the other end. There's all the metering and monitoring that we know exactly what it needs. And this is what it looks like on the inside. You have imagine about 6 inches of chips on top of this big belt. There's these big fan blowers that right up here. There's hot water coming from our boiler room, which is over here. And we're burning our chips and pumping that water over to these big blowers. And so it's just a big forced air system where we're forcing air through the chips, and it moves them through, say, 45 minutes or so is a typical residual time for these chips. Then we put them into this big stockpile, and we load up our trucks and send them on their way. Now, our trucks, one of the advantages of the dry chips is that they're also blown. So instead of dropping off the back of the truck where you have to sort of figure it out, here you can have a very low cost above grade storage like these big silos. And we actually just take a 6-inch hose and we pump it into the silo and up and over, and goes through all these big J pipes here at the top. And that's how it works. And we can bring 28 tons, 14 tons in our 2 different trucks. And these silos hold somewhere between 40 and 50 tons each in the typical biggest silo that we use. And all it is a slab with a silo on top of it. So very simple agricultural technology, 45 tons or so of PDCs. There's a good storage, good inexpensive storage, and that's again the advantage. You have a little bit less investment than a green chip system would be. In fact, it can be fairly significantly less, and not that much more than what a pellet system would be. These boilers could actually burn pellets or dry chips. It's just a matter of figuring out what the best is for a situation, and generally it's physical constraints that would cause you to have a big system that burns pellets. This is your typical material handling. So again, we blow it from this truck. So this is a truck. It goes through the hose, up through a pipe, and then down into a silo. And then you've got the sweeper arm that's moving the chips around and pushing them into this auger channel, which goes directly into the back of the boiler. So that's your typical arrangement that we're focused on. This is what we call a sweeper arm or a rotary extraction device here. And here's some pictures of the actual thing, which is again an auger in an open channel, and then you've got this sweeper that goes around, and it was underneath the pile, and it pushes those chips. If you didn't have the sweeper, the chips so many would fall into this channel, and then they'd bridge up and over that, and you wouldn't see any more chips into your boiler. So you have to jostle them. You have to move them around to make sure that the chips actually get to where they're going. And typically it's just right through the wall and into the back of the boiler. That's an ideal positioning. And you'll see some variations on that, but most of them are pretty close to that. So one of the advantages is with the 25% moisture, we're not going to get freeze ups, clumping in the silo. You can imagine a big steel silo when it's -10 outside. It's pretty cold inside that silo. And if your chips are too wet, they're going to be chunks instead of small chips. So that would be impossible to get into the boiler. And obviously you're stuck for a while that thaws out. A time when you really need heat, you've got to have fuel. So that's pretty darn important. And the composting, summer heat buildup or heat buildup anytime is not really a problem. It's subtle. It's just not to the extent where you'd have the wet chips. And then mold growth is also not really a problem. So the other thing is the fuel quality is assured. So like pellets, the fuel is manufactured and quality controlled. So whatever happens, whatever comes out of our blower, we're responsible for one thing. But on the other hand, you've got good quality wood. We've judged the wood. The incoming. We don't take bad loads, and then we make sure there's no oversized pieces. And then things like the rocks and tramp metal that might come in a green chip system is gone because we've screened all that out. So some quick technical comparisons of the fuels. Again, they're across the board: 7%, 25, 35 to 50% moisture, and then the various sizes. They all are coming from regional forests. Within 50 miles is typical. Closer is probably more typical, but there's and they're all made out of bollwood. So that's the central core of the tree. Now I say all. Green wood chips, again, it's a negotiation. You can request bollwood or you can request whole tree or some variation of that. But here we have the bollwood is common in the pellets. And again, they're mixed with other things, sawdust and so forth. But again, it's very clean. Very little bark in those cases. And then, the bollwood for our dry chips, again, it's the central core of the tree. There's a lower percentage of bark, and that's to your advantage for just a clean burn. This is my favorite slide. It is shows you with 5-gallon jugs of water, how much water you're buying when you buy a ton of pellets or PDCs or green chips. So there you see with pellets with 7% moisture, you're getting 1,860 pounds of wood, which is really the fuel you're looking for here, and only 140 pounds of water. PDCs, you're looking at 60 gallons, so it's a pretty significant jump, but not as significant as if you had 45% moisture, where there's 120 gallons of water and only 1,100 pounds of wood. So that the whole fact of what am I getting when I get green chips? Well, not only do I buy all that water, but I have to boil that water off with the wood that I've bought. So it ends up being, it's a very inexpensive fuel, but you're doing a lot of negotiation with that water to try to get that out of there so that you actually get the heat. So it's just an interesting comparison. You know, it was always running through my mind here as to what does this actually mean, this percentage, and I think this shows it pretty well. Volume per ton is a big deal. Pellets, you can see it's half, at least half, you know, than what the PDCs are, and then green chips. You know, how many cubic feet per ton? Well, because it's so heavy, it's smaller. So that's an interesting variation there. But these are volume representations. If you're going to offset 30,000 gallons of oil, 461 yards or 249 tons of pellets, but then 1284 yards of PDCs, or between 1,600 for the lower moisture content and 1,900, almost 2,000 yards for the green chip. So you got to be ready for this volume. You're going to have more fillings. You're going to have, you know, a truck coming in and backing in and doing different things. So that's part of what you get with the various fuels. So obviously, you know, if you have a very simple, small lot, you don't have a lot of room for a silo, you know, pellets would be a great choice. PDCs, you've got room for a silo. It's pretty close to the boiler room. That can work out. Green chips, you're very often building a brand new building, and you're making this whole system come to life outside of your building because you've had to invest in these pits that move the product around. And, you know, I haven't shown you systems really necessarily like that, but we can go through that in another webcast, and you'll see one of those recorded. The net heat of content of the different fuels, biomass versus the various fossil fuels. 1 ton is 120 gallons of oil pellets. PDCs, 1 ton, 93.6 gallons. This is general, but it's the calculation. It's what we've experienced. And then green chips, about 66 gallons of oil per ton. So that all goes in that same ratio with the water and all this. And then you can use the other fuels. This is maybe a slide you look at later on. This is interesting. And the PDCs at 125 a ton are 1203 per million BTU. And that's about the same as natural gas at $1 a therm, or propane at $1 a gallon. It's not that far. Let's say oil, it's about $1.38, I think is the way it calculates a gallon. So when oil's $1.38, that's the same price as our PDCs, where pellets are close to oil at $2 a gallon. You can see that here, that very, very close, $18. Green chips, you know, $10 a gallon. You know, is it worth the investment to get green chips? You know, at the 9.45 or 8.18, whatever, is it worth it when you can get the PDCs at $12? You know, it might be. Again, volume it speaks volumes there. So that's the big deal. In New Hampshire, we have something called thermal RECs, which I encourage every state to get because it really makes a big difference. And this is a renewable fuel. You're offsetting oil, the different types of carbon here we can talk about, but that's another whole lecture. But here we're just saying that when you have thermal RECs applied, the price drops significantly. So again, if I look at PDCs at 125 a ton, here it's 569, but before it was 1203. Huge reduction, and that's just because for every kilowatt that you generate in heat, you get a REC, and a REC is a renewable. It's a renewable energy certificate that power plants purchase because they are required to provide a certain percentage of the power that they produce from renewable sources. This used to be just solar electric, but in New Hampshire, they said, well, this is a renewable fuel, and if we can convert heat into kilowatts, which is easy enough as a simple conversion, you can generate RECs. So how many RECs do I get with a ton of PDCs? About 3. And I get about 4 with a ton of pellets, and I get about 2 with a ton of green chips. So if I sell those for $15 a piece net, then I end up with this price. So that's pretty good, and that's been a huge stimulus to people to convert, especially the mid-range. It's not something you'd necessarily do with a small amount of fuel, but when you're into the range that PDCs are typically burned at, it makes a big, big difference. And you have to invest in equipment to monitor the BTUs, but it all pays back. Here's the final thing is that the comparison, if you burn between, 1,000 and 30,000 gallons of oil, investing in a pellet system might make sense. But PDCs, it overlaps, it could even be as little as I've seen people with 15,000 gallons of oil and they convert to the PDCs. It just makes a few more years of difference in the payback. And then the green chips, 90,000 gallons, how many more? It might make sense. It's all very dependent. It's relative. These are not hard borders here between these different statements. Dry wood chip boilers, again, look like this with the sweeper arm. Looks like that. This is the interior of the boiler where it's being just fed by an auger directly into the flame. There's all sorts of safety devices to prevent burn back. There's automatic ash cleaning, self-cleaning grates, and so forth. This is the Whelen T4 150, which is a pretty popular boiler. It only comes in one size. That's 512,000 BTUs. So it's a package boiler, sort of quick to set up and quick to install, and that works out pretty well. It also tends to be in stock, or it can be. The UTSK boiler from Schmid is another dry chip boiler, and it obviously it's a great boiler. It tends to be in those larger sizes though. So starting at 1 million and on up, million BTUs, so double the size of those Whelens. And we've installed them up to about 6 million BTUs. So they're wonderfully clean burning. They're very efficient. These boilers tend to run in the 70-75% on up to 84% efficiency. So with the dry chips, it's really an excellent efficiency. And I'm not here to talk about these so much, but I wanted to at least show it to you. Some of the things beyond the efficiency and the reliability of it is that they're very clean burning. They also have automatic ignition and buffer tanks. The buffer tank is something that, let's say automatic ignition, it allows the boiler to turn on and off, period. If it's a warm day, it's just going to turn on and get the buffer tank up to a certain temperature and then just shut off, and the buffer tank heats you, but the boiler's not on. It doesn't have to idle all the time. Some big green chip boilers, you light them on, say beginning of November, and then it runs constantly through March, which is pretty practical, but that means it's not doing the early fall and it's not doing the early spring either. So this makes a difference where you can have this. The buffer tank gives you a lot of advantages as well. So that gives reduced on-off cycling, and it's staying at a very high temperature, but you're using an injection system from that to keep the heating loop up to X temperature, and that works out very, very well with keeping this buffer tank up to that temperature. And anyway, it's a good situation. They also burn clean, and we're finding that we don't need to have special emissions cleaning devices. We are able to do just no ESPs, and that can add $250,000-$300,000 to a project. So it's best that we don't put that into the project. So if you can have a clean burning boiler that maybe uses cyclones to get the ash out of the air, the states are very concerned about small particulates, so they want to make the larger boilers all have to be tested individually. And these things are passing with flying colors now, especially the Schmid boilers. All right, that's it here. I'm going to show you these Bellows, these 6 different boiler installations. So we're going to start with the simplest and then work our way up. Bellows Falls Middle School is an interesting one. It is a old school, probably 1930s. And it had already been renovated. The boiler room had been renovated, but it was an unfortunate thing that I sort of hate to talk about, but it was a pellet boiler they put in that has had a record of not being very reliable. And sometimes they just can't get the darn things to work. And it's not because of necessarily of the design of the burn, but it's the control system. And they've just found that there's not a lot of support and so forth. So this boiler, after a lot of playing around for like 3-4 years, they finally said, we're getting this thing out of here. So the bid was to go in and replace the 2 pellet boilers that they had like this. And so this is the type of silo they had. And they'd actually done this modification a couple of years prior, 2017. And what it had was there were 4 auger connections that would go into a bin inside the boiler room. And they had installed these slopes because they were just relying on the pellets to sort of fall into these holes. And they found that they were in there raking to get the pellets down because they didn't have any slopes. It was a flat bottom. And that didn't work great, but this is what it was. It was a circular steel, corrugated steel silo indoors, which was kind of weird, but it was a pretty simple way to put in a silo. So why not, even if it's indoors? And this is the way it was laid out, where you had these 2 pellet boilers, and then you had this auger system coming in that sort of combining everything, coming in from the silo that was sitting over here on the other side of a stairwell. So the auger actually came underneath the stairwell and then into the boilers. So this is the a little fact about the Bellows Falls Middle School is that their average consumption was about was probably around 250 tons of pellets. And we projected they'd be in this 385 range. And that's actually, this is how it worked out to be. It's about 70,000 square foot of building. And the plant uses LP as we converted it to dry wood chips. I feel like this is a little premature. Let me tell you about the boiler system, and we'll get back to that slide. This is the boiler that we put in, which is the Whelen T4 150. I showed you the cross section of that earlier. This is the package boiler. And it has this direct feed auger system right into the side of it. And this is sort of another view of that, the way it worked out here. So we have an auger that is running from under that stairway and in through the into the boiler room. This is a 512,000 BTU boiler. And we renovated that silo, the steel silo, by putting one of these rotary extractors inside of it. So that's then pushing we were able to use this silo, which was built for pellets, but now we're able to do dry chips. And that was their desire. Now, it's a slightly smaller silo than we'd often recommend, but it was, again, pre-existing. So we just have to pay attention and make sure the deliveries come at the rate that we'd like them to do. So I'm just going to go back and say again, in the end, we've been delivering to this for a year now. In the first year, they burned 385 tons of dry wood chips. So that was about 48,000. The equivalent of that is 36,000 gallons. That would have cost them about 90,000 at 250. Obviously, 72,000 if it was $2 a gallon. Who knows what the price of oil is going to be at any given year? But there was a fairly significant savings. This being Vermont, they don't have thermal RECs. So this worked out pretty well. They really didn't do any other improvements other than just to change out these boilers at this particular project. But a pretty simple installation, and it reflects, this easily could have just been a small school that has a silo outdoors with that 512,000 BTU boiler. Stevens High School has been around since around 2014 we installed this. So it's kind of a retrospective to look at this. It's a school that went through extensive energy renovations at that time. They used an energy performance contractor to be able to pay for all of this. It was a school district that had a hard time improving their schools because the town is not wealthy. Claremont, New Hampshire. The Claremont decision was all about low funding for various towns, and they were very sensitive to any kind of expenses in their schools because it was just too hard to justify. Here's the existing boiler room. It's one giant room, and it had these 4 H.B. Smith steam boilers in it. One was inoperable, so that was ignored, and the others were just taking up tons of space. And each one of them rated for 3.68 million BTUs. They fired at 2.7. So the 3 of them were actually worth about 8 million BTUs if they were all firing at once. Now in schools, you do have redundancy typically, but this was a pretty big overshoot, especially now that the building's going through renovations, energy renovations with new windows and lots of changes to the distribution system. There was also a 10,000 gallon underground tank that was installed in 1987. So it was starting to see, it was kind of antique and suspicious. You always have to be a little suspicious of a tank of that era. So here we are, the existing fuel consumption, about 39,000 gallons of oil a year. And so that would be about that 97,000. And the new wood fuel consumption with the dry chips, you're looking at 21,000. And with the equivalent in oil, that was, that there's a big difference right there. So this would be, here you're looking at, whatever, I'm not sure. This was the first year wood consumption, 168 tons of wood chips. What you also see is that there was a huge reduction in fuel consumption at this place. So that's very significant, very significant. And that was all because of those energy retrofits. We also don't have the fact of how much oil is being burned in, or the LP in the new LP boiler. So that's a question mark. I can't really tell you what total success they had, but in the end, they lean on these as much as they can. That's the priority, with the least cost fuel. So, pretty significant. This also it's able to utilize the thermal RECs, and that's not noted here, but that would reduce their cost down to about $20,000. So it's a huge savings every year with all that they've done. They're really seeing that kind of a benefit. And here's the drawing here just of the system that they installed. This is one of those pre-drawings that they laid out inside this very big boiler room, thinking they were going to go with 2 oil boilers and 3 of the sort of big earlier generation packaged pellet boiler, or I should say dry chip boiler. So this is another picture of another approach that they came up with. So it's a sort of evolution, but this one now included a silo indoors, which that prior one actually had a silo outside of this wall that had to be built. So new concrete construction for that. So the whole idea is to go as least cost as you can. And they might have underfired this a bit. We might have gone with a slightly larger combination of boilers, but here it's about 1.2 million BTUs overall. But there's that silo behind, and we had to fit a buffer tank in there, and we had to have a new gas boiler in there as well. So that's actually oil, it says here, but I think that is gas. So you end up with a rather compact space, but you're making use of that big boiler room in a way that makes it very cost effective. So here's the storage area. You can see it's a big welded steel, big tank that was assembled inside that boiler room. And it has this couple of ports on the outside that they can blow either pellets or chips. This was actually built at a time that we were not manufacturing the dry chips yet. So their first winter, they actually went with pellets, and their second winter as well. They weren't so sure about these dry chips, but we had actually fabricated these with rotary sweepers inside, even though it was intended to be pellets and spec'd out as pellets. And we said, well, we can make that change if you want to. And they finally decided, after they saw the results of other places, they said, well, okay, we'll try those dry chips. And it worked out pretty well. All we had to do was make a couple of adjustments. The difference between pellets and chips and a rotary extractor is you have to put a cover over the top of that gutter that the exposed auger is in, because if you have enough pellets on top, that actually stops the auger. They're not strong enough to turn with that kind of hydraulic pressure on it. Chips don't give you that kind of pressure, even though they're heavier. But the pellets really put that kind of force on it. So we have to just make that one change, and we're off to the races. So here's the school. This is the fill pipe right here. Very often he pulls up into this bus stop here, and he runs his hose across, or he'll go into this if it's during the daytime. He can get away with this, but otherwise in the morning, he likes to get as close as he can. But it's pretty congested, and that's the nature of, say, urban schools. And that was why it was great to be able to put everything inside this giant boiler room from this 1920s vintage school. High Mowing School is another early system that was installed about 2014. And it's a big campus, not huge, but it's a private school. And it has these multiple buildings scattered about a fairly sizable lot. You can see this. That's the main building right here that we looked at in that earlier picture, this one right here. So, and then there's this other sort of fancy building that has the octagonal shape. Then there's a gymnasium right here and some dormitories and other different places, an art studio and so forth. They had 9 existing boiler rooms, and we turned it all into one boiler house. So they were at a point where these were all about 20-plus-year-old boilers. They were looking to replace them in the next 5 or so years. Each individual boiler room, there were some 12 boilers overall. And it started to look kind of desperate. This was not a real wealthy, well-endowed campus. So they said, well, maybe what we can do is locate a new boiler house. We proposed this, and they accepted that idea. So the boiler house was put right here, and then we strung pipes from that boiler house to meet all of these different locations, and create a big heat distribution loop in a district heating system. So it was our first big district heating system that we installed, and we had to build the building, install the silo. It was all a pretty new experience here. This is one of our first dry chip projects, and we assembled the whole thing. The finances worked out well for them, and it was mainly because of the dry chips, and we were able to work out a special deal with them that they didn't have a big upfront investment. It's a private school, so that we had a tendency to look kindly on them. This is the boiler room. We've got two of these same boilers, that just the same size as the ones at the Stevens High School. And they've worked out to be fairly reliable, good systems. That they've actually changed to that TX boiler that I showed you first on the first project. But it's basically a very similar kind of boiler, just a different design, same output. We have two gas LP boilers as backup. Peaking and backup is the way we put it, so that when it gets really cold, these are generally undersized for the -20 that you might experience on a campus like that, and also for quick recovery if things have been set back over a weekend and you have a pretty cold morning, you're trying to get going on a Monday morning. You'll need to have that peaking system to help out, and that's what this is. It's all designed to react. These are secondary, and these are the two primaries. The buffer tank is being heated by the two biomass boilers. So that's this big, it's about a 2,000-gallon buffer tank sitting in the corner there. And then we've got all these high efficiency pumps that are moving the water out into the campus. And here's the blueprint of the system. This might be better to look at later on, but you've got the two tanks, the two boilers here, the gas boilers, and then the two of these dry chip boilers, the big buffer tank, expansion tanks, and so forth. And this is generating thermal REX, so it's got a lot of there's a BTU meter involved with this, as well as the regular control system to run the district. So it's been a very good success. They've all been keeping very warm, and they don't feel quite as guilty as when they're burning oil. They'd like to burn something green and local like this. So this is what it looks like with the boiler house and the two big silos beside, one feeding each of the two boilers. This is a design we'd easily use again. Perhaps we'd go with slightly larger silos just because of frequency of load, and all this might go with a single big boiler. It'd be another way to go. Instead of having 2 500,000s, go with 1 million, or even 1.5 in a situation like this, because they're being taxed pretty hard with the design load there. So here they are, just going right from the silo sweeper arm right into the back of the boiler. Boom, boom. And this is a Bellows valve here that protects you against having any kind of burn back. There's a lot of other equipment here that we don't get into here today, but that's for boiler efficiency and clean burning and so forth. And here he is, loading the chips into the silo, the blower truck. So here the prior fuel consumption was around 42,000 gallons of oil a year. So they'd be spending the 105,000. The new wood fuel is in the range of 48,000, and you've got that 250 a gallon equivalent here, so you're about half price of what you would be. And then if I add in the thermal REX, you're going to drop this price that much further. So you're actually going to be about $24,000 as a net cost, and versus what it would be with oil. LP, the equivalent of LP, whatever price that might be, there's all these different variations on the fuels, and it's we can get into that, but it's it's a payback. It's a good payback. The next one is Filtrine manufacturing. This is about a 3 or 4 year old system. It's in Keene, New Hampshire. It's a manufacturer of very high efficiency water filtration and cooling system. They make some real fancy drinking fountains that you might see in the downstairs of a fancy hotel or office building. This is their operation right here. It's in Keene, right off of this big traffic circle on Route 101, right behind the Best Western. So it's a central location. Keene is kind of notorious for having inversions in the wintertime, that people burning their wood stoves and so forth. They end up clouding up the sky a little bit. But this is a very clean burning system compared to wood stoves. And, you know, we'll talk about that. But here's the existing boilers. They actually were good enough to keep, but we actually ended up replacing one of them as part of this project. Just it was failing and had some trouble, and we changed that out. Those are the old circulator pumps, and we changed those out as well. This is what they were, and they really draw a lot of electricity. They're running 24/7 and at full speed. They did put a variable speed drive in, but just the change to these new Grundfos magnets, it's pretty amazing. So we went for those as well. This is the blueprint of the new system now. What they did is, instead of going to the existing boiler room, which is at the front of the building, we just went to the back of the building and found a corner of their warehouse that they could devote to a new boiler room. And then we joined the two together by putting in a central loop that would attach the two boiler rooms. So you could have the backup heat coming from the oil boiler room, but the dominant heat coming from this one single Wiesmann boiler that we installed. You see, C&S Grocers, they're actually renting a space in this same big building. Filtrine is mainly the occupant of this building. So here's the new boiler room with the new Wiesmann boiler. It's 1.24 million BTUs, and it again burns the dry chips. You can see all the elements here where the augers coming in from the silo that's just adjacent to the building. You've got the big Bellows valve and the direct feed into the base of this boiler. This has an automatic ash extraction system, which pulls all the ash out of the base of the boiler underneath the burner and pushes it up inside of this ash can that has wheels on it. Pretty easy to move around and empty that ash. That's a task that a person would want to do about once a week, at least, to check on it. These are big enough ash cans you could get by with longer, but you never want it to overflow because that backs up into the boiler and causes no ends of problems. The buffer tank here, it's like 1,500 gallons. This is the 1.24 million BTUs. It's all a ratio between the size of the boiler and what you need for a buffer tank. This is the cyclone that comes out, that sits separately from the boiler. And so the smoke comes out of the back of the boiler, goes into this. It spins the smoke around and extracts a lot of particulate final stage, and then goes out the chimney. So this is a very clean burning boiler. We've had great luck with the Wiesmanns. The dry wood chip storage silo, right out back, you can see that it's right up against the building, just a simple slab again, and gets filled by the truck. Pretty straightforward affair. And again, you'll see these types of silos now all the time. This flat wall silo has become our standard, and this one holds about 40 tons of chips. They have a building management system that they modeled the boilers in. They have the two oil boilers, and they've got the chip boiler here and the buffer tank, and they're reading the stratification on the buffer tank, and they're able to be notified of faults. The boiler system has this on it, but they also can take that information using Modbus, and they put it into their building management system, and this works out very well. He also has the BTU meter on this that's monitoring for thermal wrecks, and that makes a big difference. And here's the new pumps, the new high efficiency variable speed pressure temperature sensing Grundfos pumps that are pretty awesome when it comes to energy efficiency. So here's the calculations for Filtrine, and we've got this 100,000 square foot building. The existing consumption was somewhere around 25,000 gallons, and The new wood consumption is 315 tons, and at the price, it would be $39,000 for that. Less the thermal RECs here, we've got them at 16 net. You're looking at 15,000 credit back to you. These are sold, a few months after they're generated. And then the net cost of the PDCs would be 24,000. So that would be, the equivalent here. So very, very nice arrangement there for payback. And he's very satisfied. He figures it's going to be paid for in about 7 years. This is a chart that we put together for people to explain what their potential savings are going to be, because there's a lot of variables when someone's just trying to figure out whether this makes any sense or not. So you end up starting with the project cost. There's rebates involved, sometimes a grant involved, whatever. But you can subtract a rebate from this for pellets, and then you get into this net project cost. What's my coverage? I'm somewhere around 92%. And then what does that mean? Well, 92% biomass coverage, 193 tons of pellets or 250 tons of dry chips. So we work this out. You've obviously got to burn some oil in the end. So you're going to have this percentage. In this case, it's 8%. And then you get to choose the price of oil. What kind of price do you want to look at? There's an average, a long-term average that I think is fairly close to 275, but it's all relative. We have to decide what that is. It could be 250. And then you add the thermal RECs in, subtract them actually, and then end up with your net price of, and you look at the cost of the project, the net cost of the project plus the ongoing annual cost of fuel, and 10 years, including both, on all 10 years of fuel, this is what you're spending. So it's just a way to compare. This doesn't directly relate to that other one. This was the chart that we actually used when we talked to them. So there's some variation from this to reality. But in the case of just sticking with oil, they could have stuck with those old oil boilers or replaced them in the next few years. And that's what we figured, that there'd be about a $90,000 cost to replace them. That's included in this price. So, it's all relative. All the numbers are there if you want to play with them and see, well, maybe if I don't want to replace these, I want to stretch their life and only spend $10,000 keeping them going or something. All those things are possible. Change the price of oil, change the price of fuels, whatever it is. So it's a neat way to look at it. And here's the way it looked like in a chart where you can see the ongoing. Each one of these has that initial cost of system, plus it has the price of the first year's fuel in there, including the oil or whatever it is, and then it projects it straight out. So here's the oil. The black one starts out cheaper, but very soon it crosses. And the first one it crosses is the PDCs, say at about 5-6 years. And then the next one it crosses is well, we actually had the green with sort of an add-on where we said, we'll throw in an oil boiler, and that's obviously going to increase your expenses and your payback. And then we can go to pellets. And you can see pellets were more like 8-9 years. So, this pays for a lot. It's like a lot of energy renovation, is that you can do some different things with your savings. And, a 6-7 year payback is better than a lot of other energy things you can do. And, something even like solar, you'll find that the payback is not quite as nice as this. So that's an interesting one. There's number 5, and that is Wheelen Engineering. And it's actually 3 projects in one. It's in Charlestown, New Hampshire. It's a big manufacturing campus. But the first place that we talked to them about was a new building they were putting up. Now, Wheelen, if you've ever heard of Wheelen Engineering, you might be, if you watch car racing, whether it's stock cars or Indy cars or this kind of Monte Carlo car, that you have a flashing lights. All the flashing lights that they make are used in these kinds of racetracks, airports. It's a very interesting company that makes just about everything that they put out, police flashing lights and that sort of thing. They actually manufacture every component right here, from resistors on up to the plastic housings. So it's a big operation. They employ about 1,000 people and sits on the river over by Vermont. And this is the plan. The initial plan that they came up with was real fast. This place was, the building was actually up, And they said, we want to add a boiler room to be able to burn some, biomass here. And these were people that Mark, it's actually our first negotiated project, and for the dry chips. And we thought about doing the dry chips back in 2012, 2013, and we were looking for somebody that you got to have a customer before you actually can make the chips. The customer needs to have the chips made before they'll invest in a boiler that's going to burn them. So we said, listen, if you buy this, we will make the chips. We commit to that, and we'll sell them to you for X price. And they said, okay, we'll do that. So they proceeded to very quickly build this boiler house that was to this spec. Basically, it's a boiler room here in the blue, and then these individual silos behind each one of the boilers that would be located 1, 2, 3, 4. And this is where the chips would be loaded in. There's a big buffer tank located here, and this is the way it all worked out. It's very, very close. The mechanism that feeds these is a little changed, but that's not a huge significant change. 4 stacks in a row, the way it works. So here's the way the boiler room looks. 1, 2, 3, 4 in a row. Beautiful piping, beautiful brand new room, nice and bright. Boiler rooms don't often look this good. This is the door into the silo. If you wanted to check and see your chips and the sweeper arm and all that, that's all inside here. 1, 2, 3, 4 in a row. And, really a beautiful system when you get down to it. There's bin level sensors that are like a radar sonar that tells you how full these things are by percentage. Again, you've got your auger coming directly into the back of the boiler, and a very tidy arrangement. It couldn't be nicer. There's the sweeper arm with some chips on top of it, and a square silo with a round sweeper arm. It works. You have a little bit of residual in the corners, but it's not a really big deal. It just, it works out pretty well. On this first installation, we thought, and they thought, we ought to have a delivery method other than blower truck, since we didn't even have a blower truck. It was the concept, but we didn't have one yet. And so they said, well, tell you what, let's make it so that we can receive this with a live floor truck. So that means this garage door opens up, the guy backs in and dumps his load into this blower. It's a rotary system, and then not blower, actually. It's a bunch of augers that just feed it outward and up into those silos. And that's what this was all about, is that this is actually a big central auger that feeds each one of these bins. And, we had your ability to sort of manage that, and it got pretty complicated, but it was done. And then in the end, the blower truck arrived, and the first year they actually burned pellets, and we put these pipes in so the pellet truck could blow them, as well as we could blow once we got a blower truck. So this is actually the method that's used. This kind of sits there doing not very much, because they're buying their chips from us, and they're buying them, get them delivered with a blower truck, and it's just so much easier for everybody. So here's the new, the first system was a 250,000 square foot production facility that was, brand new, pretty nice. And there's also, actually, this production facility was smaller than that. There was an adjacent building we're also heating within that. So we put these pipes in, and the Wheelen Engineering site is shown here. And I thought it was kind of neat that the Connecticut River shows up right there. And it's just across this Route 12A that goes through the middle of Charlestown. And this is the campus. This building is actually now expanded, and let's go to the big picture here. This is the campus. This is the main original building. This is where the new building was being built, where we put in plant 1 right here on the end of it. And then this was that extended area that was the manufacturing plant that we were also heating. So you can tell this is much bigger than what that is. And so we're heating all of that with this big district system with that 2 million BTUs. And that's a big load for that one plant. So there's a lot going on here. Plant number 2, we put in right here on the side of this building, and it was identical. I'll show you that in a minute, identical to the first one. And then finally, a couple of years went by, and they said, we want another plant. And they built a brand new building just for the boiler plant and the 3 silos on the side. And then that plant joins into this district. Does not heat these 2 buildings. That's a district of its own. But this joins into this big section here and heats this building. And they have the projections of some other buildings coming in the future. So it's a pretty progressive company, and they have this big park of their own there. So here's number two. Again, you could barely tell these two apart except for some variations in the way that the building looks. But that's the four Froling TX 150s that are 512,000 BTUs maximum each. So just over 2 million BTUs total output. Big buffer tank, just identical. And here it sits there with the stacks sitting up there. And this is just one of those days where everything shows up because of the humidity levels. And it looks like we're just smoking the place out. But these are just ventilation units. And then we have a lot of moisture coming out of our stacks. That's what shows. So here's boiler plant number 3 then. So here we are again looking over at boiler plant number 2, and way over here is boiler plant number 1. But here's this sitting up on this sort of hillside, and there's our truck filling up the silos. So you can see we fill it with this long hose, 1, 2, 3. They have to climb up on these ladders. This is actually a stairway. Our guys tend to prefer a stairway now instead of just a ladder that goes up the side. So we take this, and then there's this gangway that they can go and look inside each one of these silos. We haven't really gone the route of having like sonar detection or anything of the levels. We tend to find that things just get silted up or, with dust on them. And so they become less reliable. So we've tended just to go manual. Our guys don't mind going up, and they're really the ones that are monitoring the fuel in most of these places. They start to get a pace, and they'll come in and they'll top off and all 3, they'll fill up all 3 with a big truckload. Not fill, but they'll top off and figure out which one needs the most and that kind of thing. So that's managed. This is, again, the way the plant looks here. Now you got 3 of these boilers in a row. Now these are that same Viessmann boiler that was in one of the earlier ones. And these are worth about 1.7 million BTUs each. And 1.7, why is that? Well, in New Hampshire, you can sort of go below the radar and not have to have testing done on your boilers, but these are rated boilers with certain fuels. They've been tested by the factory, and you still have to show that you're going to be a valid product for meeting the criteria, but it doesn't require that you have on-site testing. And so they wanted to sort of fly under the radar with that. So they put 3 of these in just at that 1.7 mark. So what does that end up being, like 4.2 million BTUs or so total? And now this is doing most of the load. They've diverted away from the 4 boilers on boiler room number 1, and this does most of the load, but they obviously keep that other one going. So here's the way it looks from another angle. This is the master control panel that manages all 3 of these. Each has a panel like this, but this is the one that does the centralizing and the staging and so forth. And so you get all this data on their screens there. This is the cyclone again, just a different angle on it. Comes out of the boiler, goes into the cyclone, and then up and out the chimney directly. Big buffer tank. Nice layout. The buffer tank is in the far corner. So you might have seen right here, that's the buffer tank, and then the 3 boilers. Just a long corridor, easy servicing, easy access to everything. So very nice, just ideal. They've done the best boiler rooms because they've all been executed as brand new boiler rooms, even if it was an existing or situation. So that's good. Now here's some guys that are heating 500,000 square feet. Their wood consumption, 2116 tons of PDCs. That was what they burned last year. It seems like it's an ever increasing number, but that's huge. And you can tell that's the equivalent of 198,000 gallons of oil that they're not burning as a result of burning the PDCs. We find that's pretty commendable. So they're spending now $174,000 on the net cost of these, but 495,000 or 400,000 basically. So they're saving over $200,000 a year, depending on what they might be negotiating for the price of oil, not considering all their other difficulties with the tanks and all that. So it's just a great situation. It's a very stable price. We haven't fluctuated more than $5 on our cost of fuel, and the tremendous savings. great stability. Okay, number 6 is the University of New Hampshire, and that's in Durham, New Hampshire, where the big university is located. And this is the Thompson School area, the Thompson School of Applied Science, and it's called the Northwest Heating Plant. Let me explain. The Thompson School in this whole area includes the different buildings. There's Barton Hall and Cole Hall and Putnam and the veterinary lab, as well as these big greenhouses. So these are some of the views. There's a veterinary lab down there. So the different views of these locations. This is, think of UNH now. This is the entire campus, and it's a big campus, and it's being heated now by a central steam plant. I think they have hot water and steam coming out of that. They're generating electricity as well, as I understand it. So the idea was that this plant sits there, and it's fueled by gas. It doesn't have biomass, but it's a gas plant. So again, that eliminates a lot of separate boilers and all the different buildings, and they have this big existing system there that's been there for a good long time. You know, if it's 30, 40 years, I'm not sure exactly how long it's been. So here's what we're talking about, is that this is the field house, and I think that is definitely still being heated by this boiler house, this central heating plant. But what happened was that these pipes were starting to corrode, and they had a long distance to go to change them out. And they said, listen, if it's going to cost us X amount of money to just replace a pipe, why don't we consider an experiment with biomass and do this district right here that's sort of off by itself. They've never been really happy with the amount of heat that they're getting in these far buildings, because everything, the greenhouses on a cold day, they took all the heat, and there was not much left when it got to these guys. So that was a problem. And so the decision was made to get a bid and see if they could cost justify putting this all on a separate heating system. It also gives this plant a little room to grow, maybe in another direction with new buildings they might consider. So it's all looking for the future. So here's that close-up of where the field house is and all this. But again, we're cut off. This cuts off right here. So this is no longer being heated, and it includes these greenhouses, this hall. This is the veterinary building. This is the Putnam Hall, and the Barton and Cole buildings right here. We are not heating the visitor center, the stables. It's all just this one small district. So that was the plan. They asked for us to come up with some ideas about how to do it. It was a sort of a design build approach. So we came up with this idea. We had a few different options, but this is the one that won in the end. So we went in the corner right here of where these buses are parked right here at Putnam Hall. That's in this section right here. So we basically just filled in this gap with a boiler house building that actually stands separate. It's a little bit separated from the existing walls there. And so it stands alone. And you can see that it's got a lot of space in it, just a nice layout for the boilers. We actually rearranged it a little bit once we really got into it. But this boiler now sits here, and then these two boilers are down in this direction, and there's no garage door here, I don't believe. The silo is still in the corner, 20 by 20 foot by about 24 foot high silo, built out of masonry. So this was all fresh built masonry, nice exterior, nice design, a one-line drawing of the new system. Again, you've got the 1,000-gallon thermal storage tank. It's only a 1.7 million BTU hour boiler, so that seems small for this, but it's under a big load. They also have the gas boilers, which are natural gas. I think they have the option to put some of their swamp gas. They've got like dump biomass gas from a dump that's about 15 miles away that fuels the big plant, and I think they're able to sort of mix that. But either way, this is the way the plant's set up. Pretty straightforward design, and this is the result. Really attractive looking building with the rolling truck. Looks even better with the rolling truck out next to it there, blowing chips into it. But that's the fill pipe. It goes up and over the roof and over to the silo and down inside. Here's the boiler room, a beautiful, clean, shiny floor with a big Wiesmann No, that's funny. That did say it was 1.7, but I'm mistaken. And in the end, we ended up using the UF boiler from Viessmann, which is a little bit more efficient, a little more adaptable, and 2.457 million, about 2.5 million BTUs, the 720 kilowatt model. So again, a lot of the same features. You can get into some of the features. This is all self-cleaning. This is a pneumatic system, and really just a nice clean design. One of the neat things about this, you can have a nice clean boiler room like this. You'll get some dust certainly in a boiler room, but here the silos all enclosed. The fuel really isn't seen inside the boiler room. It's all inside enclosed augers being fed from the silo directly into the boiler. So you can keep your boiler room actually fairly clean with just a little bit of dust here and there, but it's certainly not the degree you would have if it was an open chip system. And there's the silo again. It's coming right out of the sweeper arm and then right into the mechanism that feeds the boiler. So pretty straightforward affair. And there's the silo sticking up over the top of everything, silo in the corner. It's a couple of views. They wanted to be able to demonstrate this to kids in the school, make sure that it was a teaching experience as well, and that they also were collecting data and viewing it very readily from the operations office as well. And this is what you see from some of the boiler management software, is that you're looking at the stratification in the buffer tank. And this is all designed to really encourage that stratification. Here it's only about 4 degrees. And you might see that it's just a certain point in time when this was taken. But what is actually happening is the monitoring system within the boiler, the management system, is actually watching that stratification, and it's ramping the boiler up and down by what it sees. And basically that's indicating the load. But the boiler heats the buffer tank. The buffer tank, using injection, heats the loop, which heats all the buildings. And so this is always monitoring that buffer tank, and that's a very accurate way to keep things going. So here's the summary: 5 classroom buildings, 10 greenhouses, total area 150,000 square feet. The wood fuel, they're doing about 700 tons a year on average, and with the thermal RECs, that ends up costing them 54,000. Equivalent of oil would be 65,000 gallons. And if they were burning oil, they'd be saving between 75 and 107,000 dollars a year. So a pretty significant change. Versus natural gas, it's actually, depending on what you pay for natural gas is the big question. If there were a buck a therm on natural gas, it would actually be still competitive with that. But the one thing why we don't compete often with natural gas is you can't really pay for this expensive system with the savings. You can do that with oil, and that's why we tend to not do much business in natural gas area. Obviously, UNH was trying to prove a point. They're trying to use this new fuel and show it off. The forestry department is right in these buildings, and so there's a lot of good things that they're doing. This is John Stark High School that utilizes our new Schmid boilers that we've gotten a nice line of boilers from Switzerland that we feel are just a step up. And now that Viessmann has really withdrawn their boilers from the marketplace, we have this as really our best supplier and our focal point for boilers of the larger size. So we'll use the Whelen boiler still. We've got this. Okay. So anyway, here is let me show you this. This is the existing boiler room at John Stark. It was just a typical oil boiler room. And then here we are with what the setup was, is the boiler room was inside like this, and this was actually a workroom. So this is the outdoors, and so you'd have to go some 35 feet, I believe, to go from here to here, and then want the boiler. So they wanted to keep everything right in that same space. So we ended up putting just a really long auger. You can see it's a series of augers that goes from here to here to get it into the boiler. So otherwise, it's just the same. It's just an extended auger. The one-line drawing, I like to throw these in when they're available, but it's all just too complicated for me to understand. But it's something that if you get the PDF of the presentation, we're happy to include that. So here they are with their fuel consumption, 41,000 gallons, and the average price $250, and you're getting the wood consumption of 350 tons with this equivalent price here. And obviously, if we had thermal RECs in there, you're going to be something like 40,000, so $60,000 a year saved in that range. Pretty significant. But the big Schmid boiler is it's a big boiler. It's tall, but it's a big output. This is somewhere in the range of I think it's a 2.5 million BTUs, something like that, and a substantial boiler. The same kind of features that the Wiesmann has, which the air injection, because the horizontal tubes, they blast the ash out of that. And then you've got the rolling ash cans that are automatically filled and so forth. And then we used a Wiesmann gas boiler next to it that was very efficient and space efficient as well. So these two working side by side as the primary and the secondary boiler has worked out very, very well for them. And here's some pictures. Here's that auger that comes out directly out of the silo and then goes across the room, feeds the boiler. It's a little awkward to have it sitting there, but they try to make use of the space with some shelving and all. And that's just what happens. The silo, the feed back from that big auger. So it's really just a two-stage auger. Try not to get too complicated. And then the silo sits right outside the door. With the construction, we tend to not go too shy. You've got to use the right equipment to get this built right. And we tend to use cranes and lifts and whatever it takes to get these things built right. Maplewood Nursing Home's a neat one. We're going to have some features on this one, I think, in the future. We'll have certainly have the designers. We actually had a one about this not too long ago. You can catch that, but we'll certainly talk about this again. But Maplewood is just a very substantial, the 4 million BTU boiler. In this case, it was a steam system, and they converted to hot water. The fact that they're doing a total renovation of this building really helped a lot. And steam, is a little bit harder to control, in fact, a lot harder to control than hot water. And you certainly have a lot of capability when you go to hot water. So they shifted over to that, and we expect them to be in the 1,000-ton plus range for total consumption. And interesting setup. Boiler room is the old boiler room, just took over in a different way and added a couple of gas boilers as well to make sure that this whole place is kept heated reliably. It's a nursing home. It's got to be very reliable heat. So again, got the questions, and we'll see if there's any questions you'd like to ask. Happy to try to answer them. And I can always take written questions later on. You can write to me, jim@wheelenenergy.com, and I'm happy to pass them on to make sure we get the right answers back to you if I can't answer it directly. If you'd like a copy of the presentation, I'm happy to send it out as a PDF. Just write to me, again, jim@wheelenenergy.com. Air emission compliance with biomass boilers coming up next week, and that's with John Hinckley of All Four. And then I have the 28th it's a Schmid-focused presentation where I know there's a lot of innovations happening in Europe, so I'd like to be able to show those off because that's, they're a few years ahead of us, and the concepts that they're taking advantage of, that they take for granted, I think need to be shared here. And I think there's, just that different perspective is going to be very interesting. So Mila Schubert of Schmid is going to be doing that presentation.